Now that we've learned about reaction rates, we can go on to learning about a special kind of reaction called an equilibrium. We've been looking at equilibriums for a couple of days already, but now we're going to put some definitions and some terms with those concepts that we've already seen. First, we need to know, what is equilibrium? You found out, maybe the hard way, what equilibrium was when you did the equilibrium game last week. You found that you didn't reach equilibrium until the level of water in each graduated cylinder stayed constant. That doesn't mean that the levels were equal. Everyone thought that they had first reached equilibrium when the cylinders had equal amounts of water, usually about 50 and 50. But that's not equilibrium. When you continued to transfer the water, you noticed that those levels continued to change until you reached a point where, oddly enough, they stopped changing. When the level of water stayed constant, even though you continued to make transfers, that was equilibrium. So at equilibrium, the rate of water transferred to A was equal to the rate of water transferred to B. You had the same amount of water going back and forth each time, so you didn't see any overall change in the water levels. Equilibrium doesn't mean that you have the same amounts on each side of your reaction. It means that your reaction rates are equal. Equilibrium occurs when you have equal rates. Characteristics of equilibrium. There are two things that you have to have an equilibrium. First, you have to have what's called a constant property. This is something that maybe you can see or maybe you can measure. Some examples could be like vapor pressure. Think way back to last year, we talked about vapor pressure, and we even talked about an equilibrium with vapor pressure. Remember, vapor pressure is the pressure above a liquid in a sealed container at constant temperature. We talked about how some molecules of that liquid evaporate at the same rate as some molecules of that vapor condense. One in, one out was what we said. For every molecule that evaporates, one more has to condense. So you can have a constant property with a vapor pressure equilibrium. And the constant property would be that vapor pressure. It would stay the same. You could also have this with the concentration of a solution when you measure molarity of something. And with your equilibrium game, it was your water levels. Your water levels stayed the same once you got to equilibrium. With the new lab that we're in the middle of, you know your equilibrium is reached when your color stops changing. So your color is constant. The second thing that you have to have an equilibrium, or the second characteristic of an equilibrium, is opposite processes at equal rates. You have to have some kind of forward reaction and some kind of backward reaction, and they have to be happening at the same rate. There are three requirements to maintain an equilibrium. So if you want a system to remain at equilibrium, there are three things that have to be true. First, you have to have a reversible process or a reaction. We've said this already. You can't have an equilibrium if you don't have a forward reaction and a backward reaction. Second, you have to have a closed system. These are words that we've used before as well. This means nothing is added or removed from your equilibrium. A closed system, nothing added or removed. It doesn't necessarily have to be sealed, except when you're dealing with gases. If you're dealing with gases at equilibrium, you have to have a lid on the container. Otherwise, it's like vapor pressure. You're never going to reach equilibrium. But if you're just dealing with liquids or solutions, you don't have to have a lid on your containers. And the third thing is a constant temperature. We saw this with vapor pressure last year as well. If you change the temperature, that changes, for us now, the rate of your reaction, and that's going to affect your equilibrium. So you have to have a reversible process, a closed system, and a constant temperature. Symbol for equilibrium. Instead of just using a straight reaction arrow that goes one direction, we use two half arrows, one for the forward reaction and one for the backward reaction. What we're going to talk about next is what happens when you alter the equilibrium, or what happens when you change it. When you change the equilibrium, the word that we use is stress. You are stressing the equilibrium when you cause a change. If you think about your equilibrium game, we had two cylinders. We had cylinder A, we'll pretend that's on the reactant side, and we had cylinder B, and we'll say that that's the one on the product side. Even though we have a forward and a backward reaction, we can go both ways here, the reactants are still said to be on the left and the products on the right. If we make a change, also called a disturbance or a stress, if we stress the equilibrium, like we did in the equilibrium game, where this was the second part where you added 10 milliliters of water just to cylinder A, that would be stressing the equilibrium. And that would be a stress on the left side of the equilibrium, or a stress on the reactants, because you're adding more water to cylinder A. What you would see, or the effect on that system, is that the system reacted by transferring to cylinder B, remember that's the right side or the product side, some of the water that was added to A. As you continued with your water transfer, some of that 10 milliliters that you put in cylinder A got moved to cylinder B. And you saw the new equilibrium was achieved sooner. It didn't take you near as long to get to equilibrium the second time as it did the first time. And your end result was that you had more water both in cylinder A and in cylinder B. You reached a new point of equilibrium where the water levels were different than they were before, but they still remained constant as you continued to transfer the water. Some of that added water was transferred to B, but not all of it. You saw a higher level both in A and in B when you were done. And that leads us to the lab that we're studying now, or the lab we're in the middle of now. The lab that we're in the middle of now has to do with having different systems at equilibrium and then adding a stress to that system and watching how it reacts. How it reacts to that stress is called LeChatelier's principle. LeChatelier's principle says if an equilibrium is subjected to a stress, the equilibrium is shifted in the direction that relieves the stress. And some of you saw that already with the lab that we started last week with the color shifts, going from one side of the color equation to the other side. And you may not have noticed, but it always shifted to the side of the reaction that was away from where the stress occurred. Whatever you are doing to cause the stress, the equilibrium will try to fix it or undo that stress as much as it can. And so it shifts to the opposite side of the reaction. We'll learn more about this as you finish your lab, and then also as we talk about it later this week. You do have 2 articles to read for homework tonight, the What's That Fizz and the Underground Sculpture, and there's a worksheet that goes with it, and I will be back on Wednesday. Good luck!